Okay, good morning. So, my name is Babak. So, apparently I am going to be your teacher for the course. I was being informed on Thursday that this is going to be the case. And this is a little bit unusual course for me because you have two very important disciplines in mathematics, one abstract algebra and one mathematical analysis. And we have to, and then unfortunately there is no tutorial sessions for this course, which is also very strange and weird. Of course, when you do the courses at KTH, I'm also recording, might be not appropriate to say that, but in KTH everything goes fast from course point of view, and that's a little bit unusual for me. But I mean, let us do the first week, and if you are okay, I want to add 8 more lessons, okay, as tutorials, so that we are not so much stressed. But let us continue to see how it goes. And I'm trying to record my lectures. So in those extra ones, if you cannot join, apparently you can follow it up. Because you know that in this course, it doesn't mean that if I cannot finish, the questions are not coming from those parts in the exam. I have to put them on you to study yourself. Okay, when I check that. So, and that is not very optimal, especially as I heard most of you probably are teacher training in the teacher training program. And then the reason, and by the way, let me ask you one question. Do you find it luck to start the first day in the first week, the first day of the week by mathematics, or you find it bad luck? Yeah, so the laughter shows that the second one is probably the case. And of course, the reason goes back to your math teachers. I'm not saying that everyone will be able to learn and to love mathematics. Some people really love the mathematics, but some people, at least you shouldn't dislike mathematics. Okay, and especially if you are going to be a math teacher, feel responsibility for the next generation. Don't feel, and then I just want to say that in the future, if someone asks those people, do you find it luck or bad luck? They definitely say luck, okay? So, I think this is going to work. If you don't like this, teaching is not something like that. You have to like it, otherwise it's pointless. You will destroy the next generation interest in it. So I remember my daughter didn't take physics course in the high school because she didn't like the physics teacher. Okay, so people at those ages cannot recognize the difference between the subject and a bad teacher. So you should be a good teacher, okay, if you want to motivate the next generation, which is probably your responsibility. Okay, so let us see how it goes, and please try to communicate with me as much as you can, because if you answer my questions, even if the questions are wrong, I will try to adjust my level with you, okay? But for this course, at least for the first part, which is the abstract algebra one, I am assuming, because when I checked your curriculum, I realized that you have already studied some group theory in discrete mathematics. I will not take that for granted. I will start from scratch, but there are things from number theory that you have studied there. I cannot take them for, I have to take them for granted because they will not be able to finish the course. We are already in trouble in finishing this course, so let us not add to it. But at least I will recap some of the things that you need to know for every subject that we are going to do here. And I think they told me that I am going to be the examiner, but still when I check the Canvas page, my name is not under the examiner. I will actually check it out, because if I myself is the examiner, it would be more smooth for us. So because sometimes I emphasize on a subject, then you know that, okay, the chance that these comes in the exam are more than the other ones, okay? But if I want to teach something and another person is going to design the questions, it's not very optimal. It's not very optimal. But let us see how it goes. Any questions you have? Did you receive my announcement or something? Am I doing it correctly? Did you see the Canvas page? The Canvas page is still under construction because I have to prepare my lecture today because I was informed on Thursday and I haven't even signed my contract yet. So I am a little bit in a hurry, but I don't want to project this on you, so hopefully you don't feel it, and for you it goes very smoothly. And so I have changed the mathematical analysis book to a new one this time. So the information of the book is on the Canvas page. So the book that was used before was Pooh. It's a very good book. Of course, Pooh is a very well-known mathematician, but I think he is assuming that you know a lot of things already. So it's not a very good one, I mean, to start in reading. Okay. So if you don't mind, let us try to use this lesson. And by the way, I will teach 50 minutes, 5 minutes break, and then 50 minutes, okay? Because I want to go slow, not very fast. And then, let me use this first lesson to align our chemistries together first, see how it goes. Okay, any questions from your side? Yeah, no? Yeah, please feel free, okay, to ask and interrupt whenever you think you have to. Okay. So the first thing we want to talk about today is the binary operations. And I already wrote for you that the first chapter I skipped because that's a historical, but it's the history of abstract algebra. It doesn't mean it is not important, but you can read it on your own. And I think it is extremely important to read that one, the chapter, first chapter yourself, okay? Okay. So now let me start from the idea of binary operations. Okay, so binary operations is actually an abstract notion that we are making something we already know in the abstract form. For example, you have learned adding up numbers, yes? So addition is a binary operation. So why it is called binary? Because it needs two ingredients from you in order to apply. To give you some numbers. That's why it is called binary operation. So if I give you 2 and I give you 3, then you add them and the answer becomes 5. So this addition is a binary operation. It takes 2 numbers from me and gives 1 number back to me. Okay, we have other operations. So here it doesn't matter which one I give you first, which one I give you second. If I give you 2 first and then 3, you will end up with 5. If I give you first 3 and then 2, you will end up with 5. So it doesn't matter. Here the order does not matter. But this is not always the case. For some operations, you know that order matters. Yes, for example, subtraction. Yes, for example, if I say 2 minus 3, that's also a binary operation because it waits for me to feed it with 2 numbers. It's binary again, and it gives me 1 number back. But the order matters because in this case, the answer becomes minus 5. And if I do it the other way around, the answer becomes 1. Yes, so sometimes order matters, sometimes order does not matter. Yes. So these are binary operations. For example, there are some other properties. For example, if I have 2 plus 3 plus 5, is this ambiguous for you? If I give this in the exam, and I ask you what the answer is, do you feel confused or not? Yeah, but because you would say that there are 2 operations, additions here. If I want to add them, I have 2 possibilities. Either I add 2 and 3 together first. So first in mathematics means that I use pairs of brackets to prioritize the operation. And then I add 5 to it. So what will be the answer? This will be 5 plus 5. The answer will be 10. And if I do it the other way around, so if I prioritize the second addition operation, and then I write it like this, you see I am keeping the order 2, 3, 5, 2, 3, 5, 2, 3, 5. So I'm not changing the order, but I'm changing the grouping. Yes, I'm prioritizing the operations. Here I prioritize the first addition. Here I am prioritizing the second addition. But the answer will be the same. Yes. So this will be 2. If I add this, it becomes 8, and the answer becomes 10. So it doesn't mean that I am doing the same process. The processes are different. You see the intermediate processes. This is here 5 plus 5, here is 2 plus 8, but the final answers are the same. So do you know the name of this kind of property? So if an operation enjoys this kind of property, it's called associative. Yes. What about this one? If it doesn't care about the order, what is it called? Yes?
Commutative.
Commutative. So this addition is commutative and also associative. So associative means that you really don't need to put pairs of brackets around it. So can you give me an example of an operation, a binary operation, which is not associative? Yes? Now, please do not hesitate. I know that in Sweden it is not very common people talk. Many people say in their stomach or whatever you say. But please tell it. Yes?
Division.
Division. Yes, for example, let me take 2. So, if I give you this in the exam, it is ambiguous. Yes? Because it matters which one I do first. If I prioritize the first one, the answer will be 2/3 divided by 5 is 2/15. But if I prioritize the second one, so what will be the answer? So it becomes 2, it has to wait for this one to be done because it is prioritized. So it becomes 3/5 and it becomes 2 multiplied by 5/3. So it is 10/3 and you see that they are not equal. Okay? So some operations are associative, some operations are not. In order to be able to discuss all these properties on the same setting, on the same footing, we want to generalize the idea of binary operation in an abstract form. Okay? So, I give you from now on, I give you a set, okay? And then I want to define a binary operation on the set. So this is a representative of addition, subtraction, division. So I am talking about a general operation. I don't want to give it a familiar symbol. I just put a star, meaning that if you want, you can change a star with addition, you can change a star with subtraction, or change a star with division or whatever. And I want to tell you what do I mean when I say this star is a binary operation on this set. So remember, in this course, it is extremely important to understand the definitions very precisely. So, in order to even be able to talk about a binary operation, I need a set on which the binary operation is supposed to be defined. Yes? So I give you a set and I want to tell you what is a binary operation on this set. Informally speaking, I can say that a binary operation is some kind of assignment so that it assigns one single element from this set to every ordered pair of elements from this set. What does it mean? It means that if you choose any pair, any ordered pair of the elements from here, for example, I choose A from this set, I choose B from that set, and I order them. So this is the first choice, this is the second choice. And this operation is some kind of assignment. It gives me A star B, but this A star B should still be in G. So a binary operation is an assignment rule that assigns exactly one element from this set to any ordered pair coming from this set. Any ordered pair whose components are coming from this set. Is that understandable? Okay. So when I say, so it means that, first of all, let me test your understanding, repeat something. If I give you a set, for example, in this set I can have 1, 2, and 3. But this set are the set of just numbers 1, 2, and 3. If I want to construct a set consisting of ordered pairs, do you know how to do it? For example, if I want to, this is my set, 1, 2, 3. And then I want to ask, can you tell me how can I construct a set whose elements are ordered pairs, whose components are coming from set G? For example, 1 and 2 is an ordered pair. The first component is 1, it's coming from G. The second component is 2, that's also coming from G. Can you give me another ordered pair with this property? Of course we can. What's the other one? For example, 3 and 2, 3 and 1. You agree? This is an ordered pair. Or when I say ordered pair, it means that there is a difference between 3 and 1 and 1 and 3. They are not the same, even though the numbers involved are the same. So this is an ordered pair. This is the first component, this is the second component. So the first component is coming from G, it's in G. The second component is also coming from G. So this is an ordered pair whose components are coming from G. But if I want to imagine all possible ordered pairs coming from G, whose components are coming from G, what is the operation in set theory? What operation I have to do? I want to construct all. So in principle, forget about that. Can you tell me what are all possibilities? How many possibilities of ordered pairs I have? If you don't mind, let me make it 1 and 2 to make it simple to write. Okay, so how many ordered pairs I have here? I can have 1 and 1. Yes, I can have 1 and 2. Are these the only ones or I have more? I can have
2 and 1.
2 and 1. And finally I can have
2 and 2.
2 and 2. Okay? So this is the set consisting of all ordered pairs whose components are coming from the set G1 and 2. Okay? So do you have, if I give you G and in the exam I ask you to give a notation in front of it, do you remember what the notation is? No? It's Cartesian product. Yes? So do you remember? So let me just, if you don't remember, let me remind you. So if A is a set and B is also a set, A and B are sets, when I say Cartesian product of these two sets, A first, B second, it means this is the set consisting of all ordered pairs such that, this means such that, the first component comes from the first set, the second component comes from the second set. Yes? So this is called the Cartesian product of A by B. Yes? So for example here, if I change B and A, what happens? So let me give you an example. So if A is 1 and 2, B is 2 and 3. If I ask you what is A cross B, Cartesian product of A and B, it becomes what? All ordered pairs whose first component is coming from the first set and the second component is coming from the second set. So it means that I can have 1 and 2, I can have 1 and 3, I can have 2 and 2, and I can have 2 and 3. Is that right?
Yes.
Okay. But if I ask you what is B cross A, please, if interrupt me, is it clear for everyone what I'm doing? Okay, so what is B cross A?
2, 1.
The first one comes from B. So it is 2 and 1, 2 and 2, and 2 and 3 and 1, and 3 and 2. Okay? So are these two sets the same? No, they are not the same. Does they have something in common? So if I ask you, just because these things, by the way, I'm assuming that you know about them. If I ask you what is the intersection between these two sets, what is the intersection? Do you remember about intersection, union, things like that? These are important, by the way. So what is the intersection here? Intersection means the common elements. Yes, please, yes?
2 and 2.
Yeah, 2 and 2. That's the only one. And then, by the way, in the exam for this course, you have to make sure that you put the curly brackets. You have to follow the punctuation rules of mathematics, yes? So, for example, at the end of the sentence, you cannot put comma. You put full stop. There is no rule for that. That's just a grammar, punctuation rules, yes? Okay, so when I want to define a binary operation on a set, if I want to define it very abstractly, I would say that a binary operation is a function from the Cartesian product of G cross G to G. In this course, you have to learn these things. Of course, the unofficial way of saying was that, but the official way say that a binary operation is a function, a binary operation on a non-empty set. Empty set is excluded if this set is not empty. A binary operation on a non-empty set is a function from the Cartesian product G by G into G itself. So what does it mean? It means that this applies on the elements of G cross G, for example, G1 and G2, and gives you a number, an element back from this expression. This is the official way of writing it. So what does it mean? It means that if you have G, if you give me G, I cross product G by G, I get a bunch of elements, but the elements in this bag of ordered pairs, for example, one of them is G1, G2, yes, and then you have G, which is the list of elements in G, okay, and then you assign this to that element. This element here is called G1 star G2. Yes? So there are some things you need to know. When I define a function on this set, what is it called? If I have a function f from A to B, what does it mean? What is this called for the function? It's called the domain of the function. And what is B called? It's called the codomain. Okay? And there is also one more thing you need to know, and that's called about the range. So it means that when I say I have a function from a set A to a set B, what do I mean? I mean that f can apply on every element in this set A. No matter which one you choose, f can apply on all the elements, all of them. And what happens if you pick one element from here, let me call it A, f acts on it, it gives you an element in B, which you call it f of A. Okay? And this assignment rule itself is called the function f. So it is not correct to say the function f of x. Yes? F of x is the value of the function after f is applied on it. The rule itself is called the function. For example, if I say f of x equals to x squared, people in calculus, we say the function f of x equals to x squared. There are some conventions going on, but technically speaking, this is wrong. Okay? F of x is the value of f after f applies on x. Okay? So what is the function itself? It is a squaring function. The name of this function is a squaring function. This function squares every number that you provide for it, and it gives x squared. So if you have this, I am using this word effectively. So imagine that f is an operator, is a machine. You send an input in, it gives you an output back. The output is called f of, it's symbolized by f of x. But this machine itself is the function. The operator itself is the machine. That's the product of the machine after you feed it with some input. So be careful, this is very important. Okay, and if you apply f on all these elements, you get some images here. If you put them in a bag, it might be as big as B, or it might be smaller than B. Yes? That bag, that smaller bag probably, is called the range of your function. So the collection of all outputs of your function is called the range of your function. Is that right? So when I say that this binary operation is a function, by the way, is this diagram the diagram of a function? By the way, so if I draw something like this, okay, is this a correct diagram for a function? No, because a function should assign exactly one element to every element here. But this diagram is assigning two distinct points to the same point. So that's not a function. Okay? So is this one a function? This is a function, but this is not a one-to-one function. This is not an injective function. We will talk about that later. So this is acceptable as a function, but this is not acceptable. Okay, so if you have a binary operation, it means that, so let me show you the definition. So let G be a non-empty set. A function mapping the Cartesian product of G cross G into G is called a binary operation on G. Okay. So let me give you examples. Might be it would be easier to digest if I go to this example. So let us see if it is true or false. So addition defines a binary operation on n. Is that correct, or is it true or false? How should I understand that? When I say addition defines a binary operation on n, it means no matter if I choose an ordered pair, any ordered pair from n cross n, a plus b goes back to n itself. And it is defined for all of them, and this number is uniquely determined. So 3 properties. Yes? Is that correct or not? If you give me a pair of numbers coming from the set of natural numbers, and if you add them, first of all, the answer will be a unique answer. If you don't make a mistake in your calculations, all of you will get the same answer. But the important thing that you have to understand is that that answer is in the set itself. It does not go outside the set. That is extremely important. So that is, the first one is true. Yes? So the second one, subtraction defines a binary operation on n. Is that correct? No, but then if you say no, you have to give a counter example. So why is that? Because why? 1 belongs, so if I write 1 and 2, do you agree that 1 and 2 belongs to n cross n?
Yes.
But if I subtract them, the answer becomes -1, but -1 is no longer in n. So be careful, it is defined, it doesn't matter. If I choose any ordered pair, the subtraction is defined. I don't have problems with the definition part. And the answer is again unique. If you don't make a mistake, everyone will get -1 as the answer. But the third property is being violated because -1 is not in my set. So that's the meaning of a binary operation. So let us go to the next one. Subtraction defines a binary operation on the set of all integers. Do you agree the answer should be true? So because if you choose 2 integers, doesn't matter. When you subtract them, the answer is always going back to the set of integers again. Okay, so the next one. Division defines a binary operation on Q. Q is the set of rational numbers, fraction numbers. Yes, what is Q? Q is the set consisting of these numbers. So if I say what Q is the set of all fractions of this type, such that A and B are integers and the denominator is not 0. Yes? So that is called the set of rational numbers. So now my question for you, do you think division defines a binary operation on Q? What does it mean? How you think about the problem? It means, is it guaranteed that if you choose any pair of rational numbers and you divide them, the answer goes back in Q itself? If you're convinced about that, it means yes, that's a binary operation. If you can bring a counterexample, even one single one, it means that's not a binary operation. Yes? Okay, can you tell me which one do you think it is? It is true or false? False. It is false. If you say false, I have to wait for you to give me a counterexample. Yes, please.
B is 0 in the order pair that you choose.
Yes, if I choose. And this one is probably the order. For example, you say that let me choose 1/2. It is from Q. Do you agree with this? And then if I say 0 also belongs to Q, do you agree with that one as well? Why 0 is in Q?
Because A can be 0.
Yes, A can be 0. Yes. Yes, every integer is in Q because you can choose the denominator to be 1, for example. So that's correct. But if I divide 1/2 by 0, it is not even a number, so it doesn't go back to Q. So no, division is not a binary operation. Okay, what about the other one? A star B, you see, I have a lot of freedom now. I can define strange binary operations. A star B defined in this way defines a binary operation on R. I want you to understand what does it mean. So do you agree with this one? So I have defined a binary operation by the maximum of this pair. For example, can you tell me what is A star 2? It means that choose the bigger one. So this is 2. can I say, for example, 3 star square root of 3? What's the answer? 3. Okay, so now the question is, it chooses the maximum one. Now the question is that, do you think this rule is defining a binary operation on the set of R, the real numbers? How should you think about it? It means that if I choose any pair from the set of real numbers, if I do A star B, it will be a number in the set of real numbers. True or false? Yeah, because it will be one of them. It will be there. Okay, and then final one. A star B is equal to A ln of B defines a binary operation on this open interval. Yes? What do you think? So, my set is the open interval from 0 to infinity. So this is going to play the role of my G. And then I have defined A star B for you to be A ln of B. So let us check everything in detail. First of all, I have to guarantee that it is well defined. Well defined, it means it makes sense. So does it make sense on this set? Yes, because if I choose a pair from G, both of them are guaranteed to be positive. And when I feed those numbers here, I don't have any problems with that. A is defined, ln of B is also defined. But for example, if I change G to R, you can immediately rule this out. It is not a binary operation on R. Is it a binary operation on Z? No. For example, if I choose A to be 1 and B to be -1, A is coming from Z, B is coming from Z, that's correct. But if I ask you what is A star B is not even defined. Because it becomes 1 times ln of -1, and ln of -1 is not defined. Yes? So that is why I am just making a little bit more beautiful question. So I'm not giving you something in which you have a negative number. But now my question is that, do you think it's a binary operation? So it is well defined. If you choose two numbers from here, this operation is first defined. No problems with definition part. Is it unique? Yes, because if I give you a fixed A and a fixed B, when you put them in this formula, you get one fixed number. So that's also unique. But is this a binary operation? Why?
Because ln B can return a negative number, which is then not
Yes. So it might go outside G. For example, if I choose, can you give me an example?
A is 1 and B is 1/2.
Yes, A is 1, B is 1/2. So A is coming from this set, that is correct. B is coming from this set, that's also correct. But if I insist to calculate A star B, it means 1 star 1/2. It becomes 1 ln of the second one. I don't know the exact answer, but hopefully you know that ln of 1/2 is a negative number. And then when you multiply it by 1, it becomes a negative number. And this is definitely does not belong to my original set. So it goes outside my set. Do you agree? So that's it. So now can you fine-tune this a little bit so that it becomes a binary operation? So I want to keep this part the same, but I'm asking you, can you modify this a little bit so that this becomes a binary operation on that set? For example, if I change this one to this one, do you think it's binary operation? So I am changing this set to this set, and I'm asking you the same question. Do you think now it is a binary operation there? Yes or no?
What did you change?
I changed 0 to 1. Is it? So why not?
ln1 is 0.
No, 1 is not. So if 1 is not here, so you have to choose two elements from here, because when you know that if I want to include 1, I have to put square bracket. So when I put this kind of bracket, it means 1 is not included. So that example is not a good example. Can you modify your example?
Then I don't have a good example.
Okay, so what about you?
Isn't it because you need to have it be bigger than E, because otherwise you'll get something less than 1, but bigger than 0. Right?
Yes, be careful. Even though I fixed that part, but the problem is that the number now should be bigger than 1. Okay, but that is not usually, so you can make a very small number after 1 that doesn't work. So if you change it to E and infinity, then you will see that this will work. Yes?
could you include E in that set as well? And it will still work, right?
If I include E, then ln of E is 1, and then, yeah, that also works. Yes. But I want to just modify as little as possible.
Yeah.
Okay. So, yeah, hopefully you understand the meaning of binary operations by now. Yes? Okay. Now let us go to the next one. I have to speed up a little bit. So, these are definitions. I want you to know the definitions. So it is very simple. Commutative and associative operations. Yes? So we say that if I have a binary operation, a star, which is defined on a set G, a star is said to be commutative if x star y equals to y star x, no matter which x and y you choose from G, for all pairs of x and y in G. So that's commutative. And if it doesn't matter how you group them, how you prioritize them, if you have two of the same operation, be careful. This is called associative. Do you think it needs explanation here? These are very clear, okay? And then the next one, I want you to know about the left identity, right identity, and identity, okay? Sometimes there are some elements in your set that does not have any effect on any other element. For example, in addition, we know 0 is one of those type of numbers. So if I add any number to 0, the answer will be the same number itself. So this is called an identity element for addition. Can you give me an identity operation for identity element for multiplication, for example? 1. 1 is identity operation for multiplication. So that's an identity. But here we have the ideas of left identity and right identity and identity. Okay? So left identity means that if you apply it on the left, it doesn't change anything. So E is called a left identity if when I apply it from the left to any x, it gives x back to me. If E has this property that when it is applied from the left, it does not change anything, that is called a left identity. If E is something that if you multiply it from the right, it doesn't change anything, then it is called a right identity. And if it doesn't matter if you apply it from the left or from the right, and it doesn't change anything, that is called simply an identity. Is that right? Okay. So this is an example. It's a good example because sometimes people think that might be we are exaggerating things, but in this course you have to be very careful about the order in which you're applying things. Okay. So you have to learn to work a little bit counterintuitive sometimes. So here I am asking you, can you give an example to show that a left identity is not necessarily a right identity? So you see all the operations we have learned. So for example, 0 is an identity for the addition operation, but it doesn't matter if you write a plus 0 or 0 plus a, it will give you a back. So 1 is the identity for multiplication, and it doesn't matter if you multiply it from the left or from the right, it gives you a. For example, can you give me the identity element for in matrices? For example, let us say that I have the set of all 2 by 2 matrices. Okay? Can you give me the identity of the multiplication operation in matrices? Yes?
It's the matrix that is 1, 0, 0, 1.
Yes, so this is the identity matrix 1, 0, 0, 1. Okay, and if I give you any matrix, and you have seen it in linear algebra, again, it doesn't matter if you write a times I or I times a, the answer will become a. So most of the algebraic systems we have worked with, the identity element has this property that it is both a left identity and a right identity. Is that right? But this is sometimes not the case. So this example is asking you, can you construct a pathological example? You just manufacture an example that this doesn't have any property. And these questions could be extremely hard. Okay? I just want you to know that sometimes these questions are not as easy that you might think. But could you come up with this recipe? Yes?
Is it 0 for subtraction? Doesn't that work?
Subtraction for 0. So might be that's a good example, isn't it? So if you have a subtraction so yes, you are saying that if I have this set, for example, yes, if I have this set and my binary, so by the way, is it correct or not? Is the example he told us is a good example or not? Yes?
I think that 0 is a right identity, but not a left identity.
No, but be careful. So I have to change my set. So you are talking about this set probably. First of all, I cannot talk about this on this set because this is not even a binary operation there. So I have to have a binary operation first, then talk about identity. So if I want to take z and infinity, so any number minus 0 is definitely equal to a. Yes? But 0 minus a is minus a. And then you see that this is an operation, this is a right identity, but it is not a left identity. Yes? Is that right? Okay, but another example is a constructive example. So let us say that I have G, which contains A and B only. It's a very abstract example. I don't know even what A and B are, but I know that these are two different different items. So then I define this binary operation like this. These are I just want you to understand that you don't have to look for all the familiar cases. In this course, you have to be able to actually construct some abstract examples. So, first of all, do you believe that this defines a binary operation here? Because any pair you choose from here, and you feed it here, it will give you the second one. But the second one is already here. So it's a binary operation. Is that right? But now, for example, here, if I choose A cross, if A star B, what is the answer? B. If I write B star B, what is the answer?
B.
It's B. Yes. So, and then, and if I write B star A, the answer is A. And if I write B star A star A, the answer is again A. Yes? So, what do you think A is? Here, A is a left identity. Do you agree? This one and this one tells you that A is a left identity. Because when I apply A from the left to the elements in G, it will not change the element. And here it will not change it. But the other way around, it changes that. In this case, it is changed. You see, when A is applied from the right, it does not give you this B, it gives you A. So this is one example that shows that this is not the case always. Yes?
Is this not commutative?
This is not commutative.
Okay, but a binary operation doesn't need to be commutative.
No.
No. Okay.
No. A binary operation is just a function.
Okay.
Yes. Yeah. So this is also another example. Okay. So now we go to the next definition. So here, let star be a binary operation on G with left identity E sub L, and let X belongs to G. An element X prime is called a left inverse of X with respect to star if X prime star X is the left identity EL. Yes, is that clear? So if I have a binary operation on that set, yes, and then we have a left identity. What do I mean by a left inverse? So you give me X in G, I would say that x prime in G is called a left inverse when, if it is applied from the left on x, it gives me E sub m. And the similar thing is true for the right inverse. So if you can find an element that when it acts from the left on my element, it gives me the left identity, x prime is called the left inverse of x. Yes? And then if I have it the other way around, if I have a G and a binary operation and a right identity, and I have an element in G, if I can find x prime so that x star x prime is E sub r, then x prime is called a right inverse for x. If I have an identity element and this works in both directions, that x prime is simply called an inverse. Okay? In group theory, you really don't need to appreciate that much. So if you are a little bit confused, you can go and study a little bit. But most of the times, we don't need to differentiate between the left identity and the right identity, left inverse or the right inverse. Because in a group, as we will study later, you will see that all of these concepts are the same. Okay? Okay, but this example is also a good one. So let us do this one and just leave it. And then we have a break. So give an example to show that a left inverse is not necessarily a right inverse. Okay, so that's also good to understand that there is a difference between left inverse and a right inverse. This example is a little bit weird example. Okay, so let me give you a little bit of break, might be you are tired, and then we go to this example which is a little bit harder. Okay, so 7 minutes, we can have a break now, okay? Thank you.